Okay, so the derivative as a function. We have an example here where f is the square root of x. So again, if I use my little car with the headlights, I can see that the tangent line at every point has a slope that looks like this. What's happening when I'm approaching the origin over the curve? The tangent line is changing from being a positive value, and it's growing and it's growing and it's growing and it's growing and it's growing, and finally it's going to end up being a vertical line for which we know the slope is undefined, or in this case infinity. So we're going to see what would be the derivative function for square root of x. So we're going to find f prime of x when f of x is square root of x. I set up the problem here. I know that I'm going to use this particular definition of the limit. I have f of x plus h minus f of x. So I'm going to subtract these two rads. Now, what happens here, if I replace h equals 0, I'm going to have, again, 0 over 0. And I cannot find the limit that way. So I'm going to have to multiply by the conjugate. That's why I multiply the top and the bottom by, instead of the subtraction of these two roots, the addition of them, so that I have difference of squares. So this product is the square of the first one. When I square a square root, they cancel out, and naturally I have x plus h left. And then square root of x times square root of x just gives me simply x. The x cancel out because it's x minus x. And then what happens to the h here? The h in the bottom is a factor, so these two h's also cancel out. And I have on the numerator a 1, and then on the denominator these two sums. Now, if I replace h with 0, then I don't have 0 over 0 anymore, and I can evaluate the limit. So this will turn out to be 1 over square root of x plus square root of x, which gives me 1 over 2 square root of x. Notice that the square root of x is on the denominator. If I were to write this as using exponents, this will be the same as 1/2 of x to the negative 1/2. Remember, the 1/2 comes from the root, and the negative of it comes from the reciprocal because it's on the bottom rather than on the top. That's why you have on this graph, if f is the square root of x, f prime is 1 over 2 rad x. Now, as x approaches 0, notice how this value becomes very, very small, and 1 divided by a number that is very small happens to be very large. Like 1 divided by 0.5 is 2, 1 divided by 0.1 is 10, and so on. So as x is getting very, very small, the y's are growing very large. And notice how the derivative at 0 does not exist because this never crosses the y-axis. Now, we're going to study other notations for derivative. There are several ways of calling them, and some ways are more useful than others. In here I have f prime of x, and that's the one that you've seen in the section before. I can also call it y prime because remember, y is the same as f of x, so if I can call it f prime, then why not y prime? The other definition, or the other notation that we can use also, is dy over dx. You could think of it as the difference of the y's over the difference of the x's, but we're not going to use that because remember that the derivative is not only that, but also the limit as those differences become smaller and smaller. Actually, the difference in the x's becomes very small. It can also be called the derivative of f respect to x, the derivative of f of x respect to x, the derivative of f of x, or the derivative respect to x of f of x. So everything is the same thing. You may encounter some notations in books and some others in different books. This one says that this is useful. The derivative of y respect to x is just the limit as this difference of x approaches 0. Remember that this will mean that little h as approaches 0. So it is just the same thing. And this is also another notation. Remember that this will be the function, the new function called derivative. But if I want to evaluate it at a particular value, then I can say this is the function evaluated at, I don't know, 2 or 3 or whatever the constant is. Now in here it says a function f is differentiable at some particular number if f prime of a exists. So we're going to see some values of x for which the derivative cannot be found. So that's why we're going to do example 5 step by step, because you're going to see what I'm talking about here. It's asking where is the function f of x equals absolute value of x differentiable. So let's remember that absolute value of x can be defined as a piecewise. Absolute value of x is just the same as x whenever x is positive or 0, and is defined as the opposite whenever x is negative. Okay, so remember, if I'm trying to find the slope of the tangent line to a line, that is just the same thing as the slope of such a line. So what is the slope of this piece? If I know this piece is y equals x, the slope is 1. What would be the slope on the other side? The slope is negative 1. So for any x's that are on the right side of the graph, the slope is always 1. So the derivative is always 1. So f prime of x is always 1 whenever x is to the right of 0. Sorry, to the right of 0. What happens when x is to the left of 0? All these points have a slope of the tangent line equals to negative 1. So f prime of x is always negative 1 whenever x is to the left of 0. So I'm going to graph, this is the graph of f, I'm going to graph f prime here. So to the left of 0 is negative 1, and that's a negative 1, and to the right of 0 is 1. So what happens at 0? From the left of 0, the derivative is negative 1, from the right is 1. So at 0 it really does not exist, because if you remember, I'm going to use the example of the car and the headlights. There is no road that I can go like this and then suddenly like that, because I don't know how my lights, what the path of the light is here. It could be here, it could be here, it could be here, it could be here. So, and this is something that it changes continuously in a graph. It doesn't jump from one value to another value. So the abrupt change here leads me to believe that there is no derivative at this point. I cannot have a tangent line here for which I can calculate the slope. So f is differentiable everywhere except for x equals 0. And the reason why is because the change is so abrupt in the derivative from the left of 0 and to the right of 0. Those two need to match for it to be differentiable. Kind of the same idea as the limit as x approaches a value from the left and from the right. It has to match from both sides for it to be differentiable at that particular point. Then we have a theorem: if f is differentiable, then it is continuous. So this is very simple. If I can find f prime of 2, then naturally the function is continuous at 2. If I can find f prime of any number, then naturally f of that particular number exists, okay, and is continuous. And it says the converse is not true, and we can see it in the previous example. This is continuous, okay. I don't leave my pencil to finish the graph of the absolute value. However, it is not differentiable here. So this is continuous but not differentiable. But if I give you a function that is differentiable, then you know for a fact that that function is continuous. See, and I was right here. That's what slide 11 is all about. It's showing you that it's not differentiable here. There is another way for a function to also not be differentiable, and it may have a tangent line, but it happens to be a vertical one. So that's another instance in which the derivative does not exist. So we're going to see the following pictures. So if the function looks like this, like a cusp, at that point A, from the left the slopes are negative, and from the right the slopes are positive, and it changes at a so the change of the derivative of a function should not be abrupt like that. So at a is really not defined. So graphically you can see it as a cusp in the function. I know it's not differentiable there. In here, notice how the tangent line is vertical, so also at this particular point the function is not differentiable. So in general f is not differentiable because that point kind of ruins it for the entire function. Okay, if they ask you where is differentiable, then you can give the domain of f as long as you mention x cannot be a or that particular value. So there are three different cases where the function is not differentiable. You may have a corner or a cusp. You may have a discontinuity. Definitely it's not differentiable at a. Or you can have a vertical tangent. In here it's not differentiable either. So those are the three cases that we have. Okay, so higher derivatives. If I can take the derivative of a function and that returns me a function, then I can take the derivative of again. So just to say that I took the derivative twice, that is going to be called the second derivative, and I'm going to use this notation f double prime of x. If I keep doing that, then I'm gonna have f triple prime of x, and then for if I keep doing it again, I'm just gonna have the fourth derivative, so I'm gonna have a little 4 here. You may see it between parentheses of x. So it's not that I'm raising f to the power of 4, it just means that I took the derivative 4 times on f. If I'm using this particular notation, we're gonna have to write it out like this. Notice the position of the 2. How can I write the third derivative in this notation? Okay, so it's gonna be the third derivative of y with respect to x. So notice the 3 here comes after the d and the 3 here comes after the x. So this is just notation. We need to remember how to write this. So in here f of x is a cubic function. It says find and interpret f double prime of x. So to find f double prime of x, first I have to find f prime of x and then take the derivative again. So f prime of x, limit as h approaches 0 of f of x plus h minus f of x over h. So let's see how that looks applied to this particular f. Okay, so this is why we have to learn our special cases. I'm gonna have f of x plus h. X plus h is gonna replace everywhere I see x, so I have x plus h cubed minus itself, as I have it here, minus f of x, which is simply what I see, x cubed minus x. Whenever I have a sum cube, remember that is the first one cubed plus 3 times the first one squared, the second one, plus 3 times the first one, second one squared, plus the third one cubed. Minus this is what I'm gonna have. Let's see what I can cancel out. The x's can go, the x cubes can go. So I'm gonna have this left. Then the h is gonna divide every single term. So now I have the following. As h approaches 0, these two also go, so I have 3x squared minus 1, and that is the derivative, or the first derivative of f. So now to find f double prime, I just have to take the derivative of this new function, and I forget about the original.